So this little lecture is going to go over the idea of conjugate acid-base pairs and how to identify them. And whenever we're dealing with Bronsted-Lowry acids and bases, we can identify what we call conjugate acid-base pairs. And conjugate acid-base pairs are any species that only differ in an H plus. All right, and one of the things to keep in mind is these conjugate pairs show up on opposite sides of a reaction. So one will be a reactant and the other will be a product. So for example, we're talking about acids and bases, so we can take our generic acid, acetic acid, shown here, and react it with a standard base, ammonia. So both are examples from our acids bases. And in this reaction, it's actually going to be a reversible reaction, so I'm going to use a reversible reaction arrow. And so what we're going to end up forming, right, so acetic acid is our acid. It's going to lose an H plus. And then ammonia is our base. Gained an H plus. So there's the product of our reaction. And we can analyze this reaction now. And the first thing we can say is, okay, well, where's our acidic proton? That was here. And where does it end up? Ends up over here. So that H plus moved from that oxygen to the nitrogen. And we can label our reaction. So on the reactant side, we have an acid. And we have our base proton acceptor. But notice here I drew a reversible arrow, so this reaction can go in both directions. So if we think about it from the other direction, and we were reacting these two molecules, right, we could say, all right, which of these is an acid and which of these is a base? Because recall, if this is a reversible reaction, then it can also go in this direction. So in this case, what we see is the ammonium ion is giving up a proton, and the acetate ion is accepting a proton. And so if we think about that, this acetate is going to be a base in the reverse reaction. And what I'm going to do is label it as the conjugate base, right? Because it is the conjugate base to acetic acid, right? These two molecules only differ by a proton. Here we have an H plus, and here we've lost an H plus, right? So species that only differ in a proton. So acid, conjugate base. Likewise, we have ammonia as a base, and on the other side, we can label this conjugate acid. And so these would also be acid-base pairs. So in any Bronsted-Lowry acid-base reaction, we should always be able to label an acid and its conjugate base, and you should be able to label a base and its conjugate acid, right? They're the two species that only differ by this H plus. Okay. And again, one of the key points of this is this molecule, the acetate anion, is the conjugate base to a weak acid. And we know this is an acid based on our acid rules because of this group here, C double bond O bonded to an OH. That tells us this is an acid, and this is its conjugate base. And so this is going to be a weak base. And in our classes of our bases, we said the third class was a conjugate base to a weak acid. And that's what we mean by that. Okay. With respect to our acids and bases, another key definition that we should be making is this difference between what we refer to as a strong acid and a weak acid. And these have a very specific definition in chemistry. A strong acid is one that's going to undergo full dissociation. Another way of looking at that is there's no reverse reaction. So a good example of this, a strong acid, would be HCl plus water. Use a one-way reaction arrow because there's no reverse reaction. It's going to form hydronium plus Cl minus. All right, so HCl here is a strong acid. So strong acid, 100% dissociation. So when this reaction happens, everything goes to the product side, and all we have left are products, and we have no reactants left over. So another way of looking at that is this chloride ion does not undergo a reaction to push the arrow reaction back to the left. By contrast, a weak acid, right? This is an acid that has less than 100% dissociation of that H plus. So these are reversible reactions. So when we think about this, we can look at our example of, we'll go back to acetic acid, our sort of standard weak acid example. So here's our plus water, goes to hydronium, plus our acetate, right? And now notice a couple things. We drew a reversible arrow because these are reversible reactions. And again, we can label there's your H plus, and one of them went to your H3O plus. But in this case, this is a reversible reaction. So we have an acid, right? And this is its conjugate base, as we labeled above. And in this case, the conjugate base to a weak acid is a weak base. And why that is so important is this conjugate base is going to help to push this reaction back in this direction. So only a small amount of this is actually going to go. And it turns out most acids are in fact weak acids, where we'll get less than 100% dissociation. And another way of looking at that is the equilibrium constant of this reaction is actually going to lie on the reactant side of this reaction. Thank you.